For experiment 1, we're going to look at graphical analysis. So we're going to collect some data in our data tables, and we're going to use that data to make a graph. For the first part of Lab 1, we're going to be dropping a ball from a certain distance and recording how high that ball bounces. So the first thing we want to do is record the type of ball being used. And you'll see on the following slide that there is a place to record the type of ball in Data Table 1. For this particular experiment, we're going to be using a tennis ball. Next, we're going to be recording drop distances. So when we record the drop distance, what we're going to do is we're going to hold the ball next to a meter stick, and we're going to record at the distance we drop the ball, making sure to take that recording from the bottom of the tennis ball. Not the top, not the middle, but the bottom. So the reason we do this is because the bottom of the ball is going to hit the bench top. When it hits the bench top, what's going to happen is it's going to bounce, because tennis balls have that quality, right? They bounce. So once it bounces, we are then going to record how high it bounces, also known as the bounce distance. When we record how high it bounces, we're going to take that recording from the bottom of the ball, just like we did for drop distance. We're going to drop the ball at 3 different drop distances. At each drop distance, we're going to do 3 trials. So the reason that we do several trials at the same drop distance is because we're trying to get more accurate data. So the more trials you do, the more accurate your data is going to be. So if you ever want to improve accuracy of your data, simply do more trials. Once we have completed all the trials, we will then take the average of all 3 of those trials. So how do we take the average? I have the equation written below. So for the average bounce distance, which you'll see a column in Data Table 1 to record your average bounce distance, you're going to take the bounce distance that you recorded for the first trial, add it to the bounce distance for the second trial, add it to the bounce distance for the third trial. Then you're going to take those 3 that you added together and divide it by 3, since there are 3 trials. This will give you the average.
Notice we have a meter stick in front of us, and we are on the centimeter side of the meter stick. We are going to start with Table 1. The type of ball being used is a tennis ball. So you can record that in Table 1 for type of ball. The first drop distance that we are going to do is at the 20 centimeter mark. So what I'm going to do is I'm going to have it so that the bottom of the ball is at the 20 centimeter mark. Then I'm going to drop it. It is going to hit the bench top and bounce back up. However high it bounces, that's the measurement that you want to record for bounce distance. Now I'm going to do this 3 times, dropping it each time from the same distance, that 20 centimeters, and you will record the bounce distance for each of those 3 trials. The reason we are doing several trials is because the more trials you do, the more accurate your results. So if you ever want to improve your results, you just do more trials. We are then going to average those results to get the best data point for our graph.
So the first distance that we're going to be dropping the ball from is 20 centimeters. And as you can see from the video here, I'm dropping it from a little higher than 20. It's around the 21 centimeter mark for a lot of the trials that I'm doing here. Now this is just a source of error, and if you look at the questions in Lab 1 that you need to answer, one of the questions asks for you to describe the possible sources of error in part 1 of this experiment. And this is one of the sources. I didn't have a lab partner working with me, guiding me, telling me to make sure the bottom of the ball is a little bit lower so that it's at the 20 centimeter mark when I dropped it. So just be aware of that. So for this first distance in the data table, we would write 20 centimeters for the first set of trials here. And then, watching the video, when the ball drops, we're going to record the bounce distance. Now you'll notice from the video that I actually drop it more than 3 times. What that means is I did more than 3 trials. I just did this. Remember, the more trials that you do, the more accurate it is, but we only need to pick 3 of the trials. So if you'll see, I tried having it in slow motion. The first time it bounces, it went up to approximately 11 centimeters. Now I'm just using my eye here, so there's human error here as well, because that ball bounces fast and it's hard to see exactly how high it bounces in the video. So we're just doing our best guess based off of what we see. Now that next one looks like it went up to 12 centimeters. And then the third one, probably 10.5 or 11 is what I would say. So I'm going to go ahead and just put 11 here. So now this last column here is a calculation column. It's average bounce distance. So we're going to take that equation that we saw on the previous slide to calculate this by adding the 3 trials together and then dividing by 3. So we're going to get 11 plus 12 plus 11. I'm going to put parentheses around that because we want to make sure to do that addition before we divide it by 3. Now, why are we dividing it by 3? Because we did 3 trials. If we did 5 trials, we would divide it by 5. Okay, so doing that calculation, I get 11.3 repeating on my calculator. So this is the value that I'm going to want to put here into this table. Next, we're going to look at the bounce distance if we dropped the tennis ball from the 40 centimeter mark. So you're going to record this in the second row of data table 1. Now that first bounce kind of went far off, so it's hard to see where it bounced. The next one is kind of went in a straight line, so it's a little bit easier. So you can pause it, rewind it, and pick any of these trials, whichever one you can see the most clearly, and record 3 different bounce distances. As you can see, they're all in the 20 range for the bounce distances. So values I got were between 21 and 24. So you would record 3 different bounce distances of any of those 3 trials and then do the average bounce distance calculation. The last drop distance that we are doing is at the 60 centimeter mark. So you can see at the beginning of this video, I have it pretty far away from the camera, so it's really hard to see the bounce distance, but I just wanted to show you the actual distance that it's being dropped from. So for the next trials, I brought it a little bit closer to the camera. You can't see the drop distance, but you can see the bounce distance a little better, and the bounce distance is what you're recording. You can see that when it bounces, it's going up into the 30 range. So 30, my values were between 31 and 35. So you pick any of the 3 trials, any 3 trials out of the 5 or 6 that are shown in this video, and record those for the drop distance of 60 centimeters. And then use that calculation to get your average bounce distance at the 60 centimeter mark. Next, what we're going to do is we're going to take the drop distance column of data table 1 and the average bounce distance column of data table 1, and we're going to graph it. So you can see I have a little cutout of the graph paper on the slide here. Now I do have graph paper posted on Blackboard, which you can go ahead and print off and use, or you can buy graph paper, whatever your choice is. I have two separate options depending upon what your preference is. So let's just go through the steps of graphing. So we did do graphing in Lab 0. So you've already done graphing before. It's been explained to you about doing the titles, labeling the axes, how to pick an appropriate range and interval, and how to plot the data points, etc. So I'm going to go through it once again, but a little quicker. So first, make sure that you are including a title. So when you include a title, you're including it at the very top of the graph paper. So any title will do. You can title it Data Table 1. You can title it Drop Distance versus Average Bounce Distance. Just make sure that you are titling it so that I know what graph it is, because most of the experiments that we do, we're doing more than one graph. So when you post the graph, I need to know which one I'm looking at. If I can't tell, you won't get points for that graph. Next, you want to label the axes. So this horizontal axis is the x-axis. This vertical one, kind of going off here, is the y-axis. Okay, and I don't mean label them x and y. What I mean is label them with either drop distance or average bounce distance. I need to know what you're plotting on that axis. So for this particular graph, drop distance is going to be the x-axis. The average bounce distance is going to be the y-axis. And oftentimes, when you're labeling the axes, you also want to include the units. So what I mean by that is for drop distance, for instance, it was measured in centimeters. So when I'm labeling the x-axis, I would write drop distance. And keep in mind, I am writing this like with a mouse, so that's why it's kind of sloppily written. So I would write drop distance, and then in parentheses, I would put centimeters, so they know what unit of measurement that I am using. Am I using inches, meters, feet, etc.? So in this case, it's centimeters. Once you have those the axes labeled, next you want to go ahead and plot the data points. Now to plot the data points, this is what we're using data table 1 for. Okay, so I said the drop distance was the x-axis. The average bounce distance was the y-axis. Now notice we have 3 different data points here. So let's do the first data point together. So the drop distance for the first data point was 20. We dropped it from the 20 centimeter mark. The average bounce distance we calculated together on a previous slide, and that was 11.3. So this is going to be our first data point. Before we can actually plot that data point, however, we need to pick a certain range, a certain interval. So for instance, my drop distance, we dropped it at 20 centimeters, we dropped it at 40 centimeters, and we dropped it at 60 centimeters. So I need to pick an interval to label the x-axis by. Now I could go by tens, I could go by fives, doesn't matter. What matters is that each box is worth the same amount and that I can get all the way up to 60 centimeters. So I'm going to go by tens. Now this corner right here, this corner is going to be 0 on the x-axis and 0 on the y-axis. So why am I labeling that 0 on x and 0 on y? Because 0, 0 is a data point in this lab. Why is it a data point? Well, let's think about it. If I dropped that tennis ball from 0 centimeter distance, how high would it bounce? 0, right? If you drop it from 0, it's not going to bounce, so the bounce distance will also be 0. So this actually is a data point that you're going to want to use when you draw your best fit straight line. So there's my first data point. Now I said I was going to go by tens, so each of these bold lines I'm going to go by tens. So my first one will be 10, my next one then will be 20, my next one will be 30, 40, 50, so on and so forth. So I just want to make sure that I'm at least going up to 60, which is my highest data point on the x-axis column. So now for the average bounce distance, my data points go from 0, because we said 0 is a data point on both x and y, all the way up to the 30s. Because remember when we dropped it from the 60 range, the data points were somewhere in the 30s. So I'm not going to want to go by tens for the y-axis because my data range is a lot smaller and I want to use as much of the graph as I can. So instead of going by tens, I'll probably go by fives, just so I can spread out that data a little more and make the graph easier for me to read. So instead of going by tens, I'm going to have every one of these bold spaces be worth 5. So I have 5, 10, 15, so on and so forth. And you don't have to go by 5s. You can go by 4s, you can go by 6s, you can go by 7s, go by whatever you want. Just make it easy on yourself. So on and so forth. So I'm going to stop there, but you get the point. Each is worth 5, so I'm just going by 5s for each bold line. So my first data point, get a different color here, let's do purple, is going to be 20 on the x and then 11.3 on the y. So what that means is I'm going to find 20 on the x, which is right here, and then I'm going to go up until I get to 11 on the y. So notice we have 10 on the y, and then our next one is 15. So that means 11 is just going to be a little bit over this line. So I'm going to make my data point probably right here. So that's going to be my first data point. You're going to do that exact same thing with the next two data points. So for your next data point, you're going to go to 40 on the x-axis, and then whatever you got for your average bounce distance, you'll follow that up and make another data point somewhere in this range. All right, so once you have your data points plotted, making sure there are 3 of them, the next step is to do your best fit straight line. So for this one, this is a linear graph, so we are going to be doing a straight line. When we're doing a best fit straight line, the goal is to go through as many data points as you can, but you're really just trying to average them. So I don't want you to connect the dots because that's not going to make a straight line. I want you to try to go through data points, but if you can't, it's more important that you're averaging those points. So you want to make sure there's just as many data points above the line as below the line. So for instance, if these are my data points, say my other one's over here, and I wanted to draw a straight line through them. I'm going to start at the origin because 0, 0 is a data point. If I drop it at 0 distance, it's going to bounce 0. Now, if I connect the dots, this won't be a straight line, so I don't want to do that. And my line isn't going to look straight because I'm using a mouse and I don't have a ruler or a straight edge. So it would be something kind of like that. I went through one data point, or I went through 2 data points and I have 1 data point above the line. So this would be my best fit straight line. I want you to use a straight edge and make it actually look straight though. Okay. Once you have your best fit straight line, then you can calculate the slope. So this is usually the harder part for most people. So we calculated slope in lab 0, Here's a reminder of that equation. So we have y2 minus y1 over x2 minus x1. So what does that even mean? Well, what that means is we're going to pick 2 points that are on that line that we just drew, that straight blue line that I have on the graph. Pick some points that are easy for you to read. It does not have to be a data point, and it shouldn't be a data point unless that data point is on the straight line that you drew. So pick any 2 points you want. So let's say I want to pick, what are some data points that are easy to read? Say I picked this data point here. Let me do green instead. So if I picked this data point, what I would do is I would follow that down, and wherever it hit on the x, that's going to be my x1 value that goes in that equation. Now I'm going to follow that same data point over, and wherever that data point hits on the y, that's going to be my y1 value. This will be my x1 that I plug here. This will be my y1 that I plug up here. Now I need to find a second data point. So let's use red for this one. Say I pick this point on the line right here. Follow it down. Wherever it hits on the x-axis, since it's the second data point I chose, that's going to be my x2. Follow that same data point over. Wherever that hits on the y-axis, that's going to be my y2. So then you will plug these values in to the equation and solve. Now, once you plug it in and solve, do not leave slope in the fraction form. Some math classes want it to stay in a fraction. I do not. I want you to divide it out. I want you to give me decimal points, etc. Okay? So do not leave in a fraction form. Whenever we calculate slope, we calculate it on the graph. I want you to write slope equals. I want you to write the equation. I want you to put in the numbers from the 2 data points you chose, because I need to double check that slope. If you just put an answer with no work, you won't get full credit for a calculation of the slope. I want to see what data points you used, what numbers you used. That way, if you did it incorrectly, I can show you where you went wrong so that you do it correctly the next time. So let's look at data table 2 now. So the graph that we just made on the previous slide, we're going to be using that graph to fill out data table 2. So let me quickly draw a graph that we can kind of use to help show this. So let me get my data points that I made my graph from here. All right. So what you're doing in data table 2 is we're going to ignore the second part of this data table, this actual bounce portion. You can just cross that out. We're not using it. It's not graded. What we are going to use is this predicted portion. That's what we're filling out right now. So the predicted bounce. So what you're going to do for this data table is you're going to pick 3 drop distances that were not used in data table 1. So in data table 1, we dropped it from 20, we dropped it from 40, we dropped it from 60. So you cannot use 20, 40, or 60. Pick any other 3 drop distances and write those in the table. Okay, so it can be 10, 15, 30, 35, any of those. So say I pick 10, 30, and 50. You do not have to pick these ones. These are just ones I'm randomly picking. So what you're going to do is you're going to look up these drop distances on your graph and find the corresponding bounce distance and fill that in here. Okay, so how do we do that? So the drop distance, remember, was on the x-axis, and the bounce distance was along the y. So drawing sideways is really hard on a computer. Okay, so if I have, say this is my 10. So I picked 10 as my predicted drop distance. So if I dropped it from 10 centimeters, how do I figure out what the bounce should be using the graph? Well, I find where 10 is on the x-axis, and I simply follow it up until I hit the straight line that I made. Wherever I hit that straight line, I follow it over and see where it landed on the y-axis. So in this particular graph, it landed just below the 5. So if I'm using this graph here, I would say, okay, if I dropped it from 10, my graph predicts that it's going to land, or it's going to bounce approximately 4 centimeters. Okay, and you'll do the same thing for the other 3 distances. So 30 is here. I would follow it up till I hit the line, follow it over. Wherever it lands on the y-axis, that is my predicted bounce distance. So fill that in for these 3. Now, in order to get full points for this portion, you need to have a good graph. Because if your graph isn't done properly, if it's not large enough so that you can read it accurately, you're not going to get accurate predictions from it. Now the last part of the lab, we're going to be filling out data table 3. And we're going to be filling it out using a calibrated airtight syringe. So I have a picture to the right of the apparatus that we're going to be using to fill out data table 3. Now in this apparatus, we have a gas, and it's just air that we breathe on a daily basis, that is trapped or enclosed in a syringe. What we do in this experiment is we're going to be adding weight to the top of this platform here. When we add weight to the top of this platform, it is going to compress the gas. So what's going to happen is we add weight, and the syringe with that added pressure is going to move downward, compressing the air that is trapped in that syringe. What we're going to see is that as we add mass, so as the mass increases up here, we're going to see the volume of the air, this portion here, decrease. So as the mass is added, the increases the weight being applied, which is thus decreasing the amount of gas in the syringe. Also though, as this gas is being decreased, as the volume is being decreased, the pressure inside the syringe is being increased. Okay, so the more mass we add, yes, it is decreasing the volume of the gas. But since it's increasing the pressure, we're going to see the volume of the gas decrease less and less in smaller increments as each mass is added. So more mass is added, we're going to see the volume of the gas decrease by smaller and smaller increments. So let's take a look at the data. So here I have a picture of data table 3. We have a weight added column in grams and a volume of the gas column in milliliters. So for the very first row, the weight added is going to be 0. So as you can see in the picture off to the right, I have the apparatus, I have the gas trapped here in the syringe, and up here on top of this wooden platform, that's where I'm going to add the masses. But for this first data point, I'm not going to have any mass on it. So that's why I put 0 in the weight added column. So when there's no weight on top of that wooden platform, what is the volume of the gas in the syringe? So I have a close-up here. You can see the volume of the gas, and we're reading it from this line right here. Okay, we're not reading it from where the point is on the syringe, but where this line is. So you can see this is where 30, so this would be 29, right? 29, and then we have 28, 27, 26, and then 25. So the gas originally with 0 mass is at 29 milliliters. So that's our first data point. So what we're going to be doing is we just had our first data point where there was no mass, so no weights on the wooden platform. What we're going to do for the upcoming trials is we're going to be adding masses. So what I have in the photograph to the right here is I have 4 different masses. Each of these are 500 grams. Now I know they look a little bit different from each other, but I put them all on the scale just to show you that added together they are 2,000, each of them being 500. The reason they look a little different is they're just made out of different materials. So for my weight added, I'm going to start by adding just one of those masses, which will be 500 grams. Then I'm going to add a second mass for a total of 1,000 grams. Then I'm going to add a third one, so 500 plus 500 plus 500 will give me 1,500 grams. And then last, I will put all 4 on top of that wooden platform for a total of 2,000. So what we're going to look at next is how that affects the volume in the syringe. What we would expect is for the volume in the syringe to decrease. And we're going to see it decrease exponentially. Okay, so this is going to be not a proportional graph. All right, so the weight added of 500. So when I add 500, you can see the mass up here. I have a close-up of what the syringe looks like. Now notice the volume of the gas decreased. It was at 29 before, up here, and now look where it is. Make sure you're recording that amount in your data table. Next, I put on another weight. So we have 500 plus 500 for a total of 1,000 grams. Okay, so we're looking at this third row here. So at 1,000 grams, what is the volume of the gas now? Remember, we're reading from this line down here. So record what you see in using that picture. Next, we're doing 1,500 grams. So I have 3 of the weights on top of that wooden platform. Now notice in the previous slide, it was at 23 when it had 1,000. And now it only moved a little bit more by adding another weight. Because that gas that's being compressed, as more weights added, the pressure in that syringe is also increasing. So it's not allowing it to be compressed as much. So now where are we? Approximately 22. And then last but not least, let's look what happens when we add the last weight. We're at the 2,000 grams of weight being added. Now at 1,500, it was at 22. And that 22 is right here. And now it didn't even go down a whole milliliter. It went down only half a milliliter to 21.5. Now we're going to take data table 3 and do another graph. This graph, we're going to be doing weight added versus volume of gas. So once again, go through your steps. Do your title. Label your axes. Weight added along the X and volume of gas along the Y. Plot your data points. Now this time, 0, 0 is not a data point, because if you remember from data table 3, when we had 0 weight added, it did not equal 0 volume of gas. There was actually 29 milliliters of gas. So 0, 0 is not a data point in this case. You want to go ahead and plot your other data points though. And this time, there's going to be 5 data points because we did 5 different weights were added. So I'm going to go ahead and do the first data point for you. The weight added was 0, and the volume of the gas at that point was 29 milliliters. So to do this data point, it would be 0 on the x-axis. This is my x, comma, y. And then I want to go up to the 29 on the y. So let's say I went by 5s. You don't have to go by 5s. You might actually not want to go by 5s because that's going to make for a very small section of graph. But I just wanted to show the point here. So if you're at 0 on the x, then you follow it up to 29 on the y. So your first data point would be somewhere around here. Okay, and then you'll be doing 5 more data points. And in this case, they're not going to make a straight line. So for this one, instead of a straight line, we're going to do a best fit smooth line. So it's almost like connecting the dots. You kind of do a nice little curve, a logarithmic type of graph. Now, when you're doing a smooth line, a curved line, this is an inverse relationship. So as the weight is increasing, the volume is decreasing. So inverse means if one goes up, the other goes down. And that's what we're seeing in this case. The weight is increasing, the volume in the syringe is decreasing. So for this one, since it's a curved line, we're not going to be calculating a slope because curved lines actually have an infinite number of slopes. So if we wanted to calculate the slope for it, that would take lots and lots of time since the slope is constantly changing. So no slope calculation necessary for this graph. So in summary, it's just a checklist to make sure that you have everything done. You need to fill out and complete all 3 data tables using the pictures and videos provided and doing calculations if necessary. Then you're going to graph data table 1, the bounce distance or drop distance, versus average bounce distance. Make sure you're doing a best fit straight line and make sure you are calculating the slope and showing that on the graph. For data table 2, you are using that graph from data table 1 to do a predicted bounce distance. The other graph you're going to turn in is using data table 3. That's the smooth line graph that I just showed with no slope calculation for that one. Next, make sure that you turn the page of your lab manual. There are 9 questions that need to be answered and turned in based off of the data collected. A lot of the answers to these questions I have discussed in the PowerPoint, so if you need to rewatch any parts of it, please do so. Once you have completed all of that, so you have the data tables, you have 2 graphs, and the questions answered, I want you to scan and submit them to the link provided on Blackboard in the Lab 1 folder under Course Content. Last but not least, do the post-lab quiz, also located on Blackboard. Post-lab quiz is 5 multiple choice questions based off of what you did in lab today, just to make sure that you are understanding the concepts. Let me know if you have any questions.